we're going to go through two examples of rewriting exponential functions in PERT form into the form that has a b so that we can find r and so that we can draw a conclusion. What we want to be able to do is rewrite this as a times b to the t. Now the a doesn't have to change, that's just the number in front of the exponential function part, right? So we can start out here with 523 and not worry too much. The problem is this. We need to write that as something to the t, and the way we do that is using rules of exponents. I'm going to rewrite this as e to the 0.35 to the t like that. Now, I think in an algebra class, normally you would say, I want to simplify e to the 0.35 to the t and get this. But frequently in algebra and in calculus and physics, being able to go backwards is a huge virtue. What we're going to see here, right, is I now have a constant out front and a constant to the t. So what we get is that b is equal to e to the 0.35. Now I don't happen to remember what e to the 0.35 is, so I'm going to go over to Desmos and I'm going to see that it's 1.41907. 1.41907. I'm just going to underline the last decimal place so I know that. That's b. That says basically we can rewrite this function over here. Let's see here. Back over here. So b equals e to the 0.35, right? As one, this is b, and I can rewrite that as 1 plus r. So the growth rate we're looking for is 41.9. 0.41. 907, I was already thinking percentages, or 41.907%. This does illustrate something we're going to see very often with continuous growth rates. Up here they'll say the continuous growth rate is 35% a year, which is pretty much. But if you actually see how much it grows in a year, you're going to see that over the course of a year it actually grows 41.907%, which is a lot more. That's our first example of taking a PERT function, rewriting it in terms of a times b to the t, finding the growth rate r, and then interpreting it when we're done. Let's look at a decaying function this time. So when we write down our PERT function that decays, let's see, how about if we just say something like 502, yeah, that's it, times e to the negative 0.2t, something like that. And we know that's decaying because that exponent up there is negative. We want to rewrite this as a times b to the t. And we're going to, again, use our rules of exponents to do this. That's 502. This is going to be e to the minus 0.2t like this. And we have written it as a constant times a different constant to the t. When we do that, we call that constant there b. That's for base. So the base here is going to be e to the minus 0.2. I don't happen to remember what e to the minus 0.2 is, so I'm just going to go to Desmos for a second. And it looks like 0.81873. 0.81873, hold on. Equals 0.81873. Now that is the 5 decimal places. So that says that our function here is still 502. And now I have 0.81873 to the t. Now I can actually see how big the b is. So b would be 0.81873. Remember that's 1 plus r. So if we solve for r, we're going to get r equals 0.81873 minus 1. And so it's going to be negative something. Let's go to Desmos and see what it is. It's 0.18127. 18127. So negative 0.18127, or negative 18.127%. Like that. And what does that say? That says if we're given a continuous growth rate of negative 20%, it doesn't really decay at 20% per year. It only decays at about 18.127% per year. The compounding changes stuff. This is the number I'm usually interested more than any other. I want to know over the course of a year, how much did it grow or how much did it shrink? The continuous growth rate doesn't give that for us. On the other hand, in terms of biology, for example, or calculus, it's much, much nicer to deal with the e to the rate t than it is to deal with the 1 plus r to the t. So that's two examples of taking a PERT formula, rewriting it as a times b to the t, finding r, and interpreting it.